Hello everyone, this is Gary Templeton. I'm going to talk about comparing groups, which is the subject of Module 3. Comparing groups is possible when you have categorical or nominal data. We're going to talk about cross-tabulation and analysis of variance. Cross-tabulations are simply data tables that present the results of the entire group of respondents, as well as results from subgroups of survey respondents. Cross-tabulations enable you to examine relationships within the data that might not be readily apparent when analyzing total survey responses. An analysis of variance tests three or more groups for mean differences based on a continuous, i.e. scale or interval, response variable or dependent variable. These techniques are referred to as analysis of variance because means difference test results depend on the variances of measures. I'm going to cover four different types of analysis of variance. In statistics, cross-tabulation or crosstab, also known as a contingency table, is a type of table in a matrix format that displays the multivariate frequency distribution of the variables. They are heavily used in survey research, business intelligence, engineering, and scientific research. They provide a basic picture of the interrelation between two variables and can help find interactions between them. On the left-hand side, you see a blue and red distribution. You can see that the blue distribution is skinnier and taller, whereas the red distribution is wider and shorter. This means that these variables differ in important characteristics. In addition, the variables differ in their measure of central tendency. Blue is centered on 20, whereas red is more centered on 50. We are interested in the differences of the properties of these variables, for example, where they lie on the number line and how much they vary. Another way of thinking of these variables is to think of them as being two different treatments, such as pills. Let's say there's a blue pill and a red pill, and the health of patients, let's say for example, heart inflammation, differs between the blue and the red pill. This distribution plot shows important ways in which patients are responding to these two pills. We can see that the average for the red pill is higher than the blue pill because the red pill centers on 50 and the blue pill centers on 20. We can also see that people who took the red pill, their cardiac inflammation varies more than people who took the blue pill. But we want to empirically look at this and examine whether or not these differences are materially or scientifically different. Another thing that's important to note is that these variables look very symmetrical and very clean in terms of their distribution. That is usually not the case in actual real-world data, but this graphic is useful for illustration purposes. On the top right of this slide, you can see an example of a crosstab produced by SPSS. You can see that there are two factors that we use to evaluate phenomena. We have disease, there's disease 1 and disease 2, and there's medication 1 and 2. We're interested in seeing how many people or subjects in our sample belong to each one of these subgroups. We have four that have been created by this procedure. First is those people who have disease 1 and who are on medication 1. There are 91 sample members who are in that group. The second is people who have disease 2 but also take medication 1. There are 185 sample members in that group. Moving over to the right, we can see that there are 276 sample members who took medication 1 and had either disease. In the next row, we can see that there are 135 people who had disease 1 and took medication 2, and there are 257 people who took medication 2 but have disease 2, and there are a total of 392 people who took medication 2. So in other words, there are a good bit number of people, 116 in fact, who took medication 2 more than medication 1. The final column is a sum of both medications. There are 226 people who had disease 1 and who took a medication, and there are 442 people who had disease 2 and took a medication. These counts are made more meaningful when we convert them to percentages of the overall sample. This is a very basic cross-tabulation. From this, we can calculate a chi-squared test as you see below. Cross-tabulation is the most basic way to look at differences between categories in our data. Next, I will cover four types of analysis of variance: Anova, ANCOVA, MANOVA, and MANCOVA. Understanding Anova, listed first, is the core of all four methods. An analysis of variance, or Anova, tests three or more groups for mean differences based on a continuous response or dependent variable. The term factor refers to the variable that distinguishes the group membership. Race, level of education, and gender are examples of factors. From this explanation, you can see that in Anova, the dependent variable is usually continuous and the independent variable is categorical. So in other words, we're using categorical factors to predict or explain an outcome that is continuous. There are two main types of Anova, one-way and two-way. On the top right, you can see the depiction of a one-way Anova. You can see that test scores are continuous. That would be a dependent variable, and there are three categories for test scores: people with a college degree, a graduate degree, and high school. This is very basic, as we have one independent variable that is categorical and one dependent variable that is continuous. On the bottom left, we have the same thing, except we've added the consideration of another categorical variable, which is zodiac sign. To make the analysis simple, we have only depicted two zodiac signs, Libra and Pisces. We still use high school, college degree, and graduate degree, as well as our test scores, but divide the education category further into two groups, zodiac sign. In the example of two-way Anova, you can think of it as two independent variables having categorical structures and one dependent variable having a continuous distribution. So all we've done for two-way is add a categorical independent variable to the analysis. And as you can imagine, you can have three-way, four-way, and five-way Anova. All you have to do is add categorical independent variables. Here is an SPSS output of a one-way Anova. In this example, we are evaluating the birth weight, the continuous dependent variable, by four categories of smoking behavior: non-smokers, ex-smokers, smoking less than half a pack per day, and smoking more than half a pack per day. It makes sense to see if these groups of subjects in our sample had different birth weights. In effect, we have divided the sample into those four groups. Maybe smoking has an effect on birth weight. The descriptives table at the top indicates that the means of the four groups in question do differ. Better yet, it would be nice to know whether the differences we see between the groups are scientifically meaningful or statistically significant. We should expect variation among groups, but we need to know if they are unusually large differences based on the data. A good start to determining this is the table at the bottom of the slide. This shows the results of the one-way Anova F test, which is significant at 0.019 in this case, as you can see on the far right of this table. Since you may have 3, 4, 5, or more groups in your study design, determining which of these groups differ from the other is important. Therefore, it is important to realize that the one-way Anova F test is an omnibus test statistic and cannot tell you which specific groups were statistically significantly different from one another. It only tells you that at least two groups were different. Determining differences between specific groups in the sample can only be done with further testing. We call these tests post hoc differences tests because they're done after the initial omnibus F test. As illustrated earlier, the two-way Anova compares the mean differences between groups that have been split on two independent variables that are categorical. The primary purpose of a two-way Anova is to understand if there is an interaction between the two independent variables on the dependent variable. The addition of another categorical independent variable allows for this interaction test. In this example, you can see that our categorical variables are gender, male and female, and educational level, school, college, or university. This is shown in the descriptive statistics table on the left-hand side. The interaction inspection in a two-way Anova informs you whether the effect of one of your independent variables on the dependent variable is the same for all values of your other independent variables, and vice versa. This question is answered by the line graph shown here. You can see that interest in politics, on the average, does increase with educational level. In this way, adding categorical independent variables to the Anova analysis allows us to inspect additional information about interaction effects. On the bottom right, you can see that the two-way Anova produces multiple F-test results. The interaction between gender and educational level is shown in this row, and you can see that that significance level is statistically significant at 0.014. ANCOVA. You can see from this graphic that Ancova introduces the idea of a covariate to the discussion of Anova. The letter C in Ancova represents the additional consideration of one or more continuous independent variables, that we will refer to as covariates used in ANCOVA. Like Anova, analysis of covariance has a single continuous response variable. Unlike Anova, ANCOVA compares a response variable by both a factor and a continuous independent variable. For example, comparing test score by both level of education and number of hours spent studying. Test score would be a continuous dependent variable. You would try to explain it using level of education, which is categorical. In addition, you would use number of hours spent studying, another continuous variable, to explain test score. We use ANCOVA to eliminate the effect of one or more interval-scaled extraneous variables from the dependent variable before carrying out research. ANCOVA can be thought of as a midpoint between Anova and regression analysis. Like Anova, ANCOVA separates the sample into categories in order to make comparisons. Like regression, ANCOVA considers the variability of one or more continuous variables. ANCOVA is unique in that it is the only procedure that makes group comparisons while considering multiple continuous variables. Using ANCOVA, the additional covariate or covariates adjusts the dependent variable's mean value within each treatment condition. ANCOVA is also flexible enough to include a single response variable, one or more continuous independent variables, and or no factors. When used with no factors, ANCOVA will produce nearly identical output as regression. In SPSS, ANCOVA results are presented in a table captioned Tests Between Subjects' Effects, as shown here. This is the result of a test involving two continuously distributed covariates. Those are pre- and post-test cholesterol levels, and a categorical variable indicating the treatment in between the two cholesterol tests. The table informs you whether any of the different interventions were effective at influencing cholesterol levels. Put another way, whether there was an overall statistically significant difference between interventions, labeled group here. The dependent variable we're interested in is post-intervention cholesterol concentration, and the results show this result after intervention adjusted for cholesterol concentrations before intervention. The overall result is highlighted in pink here. The significance column of this row provides the overall statistical significance value, or the p-value. In this example, you can see that there is a statistically significant difference between the adjusted means at p is less than 0.001. Specifically, there is a statistically significant difference between pre- and post-intervention cholesterol among the intervention groups. Again, this is an omnibus test, so knowing exactly what groups differ and how requires subsequent tests. The obvious difference between Anova and a multivariate analysis of variance, or Manova, is the M, which stands for multivariate. In basic terms, a Manova is an Anova with two or more continuous response variables. Like Anova, Manova has both a one-way flavor and a two-way flavor. The number of factor variables involved distinguish a one-way Manova from a two-way Manova. When comparing two or more continuous response variables by a single factor, a one-way Manova is appropriate. For example, comparing test score and annual income together by level of education. A two-way Manova also entails two or more continuous response variables, but compares them by at least two factors. For example, comparing test score and annual income together by both level of education and zodiac sign. Depending on assumptions, which mainly have to do with underlying distributions, the number of outputs that may support Manova are diverse. I will cover the two basic tables necessary to interpret Manova results. The first important one is the descriptive statistics table shown at the top right of this slide. This table is very useful as it provides means and standard deviations for two different dependent variables, English and math scores. These dependent variables have been split by sample categories determined using the categorical independent variable school, or which school the student attended. In addition, the table provides total rows summarizing the means and standard deviations for all schools for each type of score. The multivariate tests table at the bottom left is where we find the actual result of the one-way Manova. Look at the second effect labeled school and the Wilks lambda row highlighted in red. In this row, the SIG column of 0.000 indicates that the one-way Manova was statistically significant at p is less than 0.001. We can conclude that students' academic performance was significantly dependent on which school they attended. Like Anova and ANCOVA, the main difference between Manova and MANCOVA is the C, which again stands for covariance. Both a Manova and MANCOVA feature two or more response variables, but the key difference between the two is the nature of the independent variables. While a Manova can include only factors, an analysis evolves from Manova to MANCOVA when one or more covariates are added to the mix. SPSS produces a number of different tables in its one-way MANCOVA analysis, but you only need to interpret the multivariate tests table to determine whether your one-way MANCOVA is statistically significant. Again, the analysis shown here assumes the data has already met the assumptions required for the test. The main purpose of running a one-way MANCOVA is to establish whether the groups of the independent variable group are statistically significantly different on several dependent variables, in this case cholesterol, C-reactive protein, and systolic blood pressure collectively. That is, after controlling for a covariate, weight. If the one-way MANCOVA is statistically significant, this suggests that there is an empirically meaningful difference between the groups of the independent variable in terms of the combined dependent variable, after adjusting for the continuous covariate, weight. For example, it would suggest that the combined mean scores of our dependent variables, cholesterol, C-reactive protein, and systolic blood pressure, which have been adjusted for the continuous covariate weight, differ between the three groups of our independent variable group. In other words, the low, moderate, and high physical activity groups. Therefore, in order to interpret the results from the one-way MANCOVA, you need to look at the multivariate test table as highlighted in pink. The different names given to each row, Pillai's trace, Wilks lambda, Hotelling's trace, and Roy's largest root, are the names of the different multivariate statistics that can be used to test the statistical significance of the differences between groups. The most commonly recommended multivariate statistic to use is Wilks lambda, and this is what will be interpreted in this example. You can see that the statistical significance value is 0.000. This is shown in the SIG column. This means that at p is less than 0.001, the one-way MANCOVA is statistically significant. That is, there are statistically significant differences in the combined health variables between physical activity levels after controlling for weight. The remainder of this video will cover Module 3 dataset activity. Use the SPSS dataset called Chapter 10 Problem 1 data. Click on the link below for this activity. Again, remember to have SPSS installed before trying this. Clicking on the link will bring up the Chapter 10 dataset. You can see that we have two continuous variables, BMI and birth weight. We also have two categorical variables, race, ethnicity, and smoking, and an interval ratio, which is maternal age. Whereas the Anova looks for differences in group means, the Ancova looks for differences in adjusted means. In other words, the dependent variable adjusted for a covariate. As such, compared to the one-way Anova, the one-way Ancova has the additional benefit of allowing you to statistically control for a third variable, sometimes known as a confounding variable, which you believe will affect your results. It is the third variable that could be confounding your results that is designated the covariate, and you include it in your one-way Ancova analysis. Using our data set, we want to test whether there are differences in infant birth weight among subjects grouped by maternal smoking status. In simplest terms, we want to know if smoking by the mother affects birth weight. So the continuous infant birth weight variable serves as the dependent variable, and the nominal or categorical maternal smoking status measure is the independent variable. We are confident that maternal pre-pregnancy BMI, another continuous variable, also plays a part in influencing infant birth weight, so we use it as a covariate in the Ancova analysis. Before we conduct our Ancova analysis, we want to know if our covariate even has a relationship with the dependent variable. As a preliminary test, we will conduct a Pearson's correlation test between the dependent variable, which is birth weight, and our covariate, which is BMI. Go to Analyze, Correlate, and Bivariate. Select our dependent variable, which is birth weight, and our candidate for the covariate, BMI. Move them both over. We're interested in the Pearson's R because I looked at the distributions earlier and both appear to be asymptotically normal or nearly normally distributed. Press OK. You can see that the correlation coefficient is significant at 0.01. It is a positive relationship at 0.560. This means our covariate probably does play a role in determining the dependent variable. More precisely, the BMI of the mother is significantly related to the birth weight of the child in our sample. It asks why this is important information. It is important because now we are comfortable in including this covariate in our analysis. The next question is whether or not the assumption of homogeneity of regression is met. There are several assumptions that should be met, and I will refer you to your book on that. The question also asks for the interaction effect between the two independent variables, specifically a factor and a covariate. Based on the description above that you see, we will designate smoking history, a categorical variable, and BMI, a continuous variable, as independent variables. Infant birth weight is the dependent variable. The third question is to interpret the results of the ANCOVA. We can run analyses for 2 and 3 together by simply running the ANCOVA. So we go into SPSS, we click on Analyze, General Linear Model, and Univariate. Again, based on the problem, birth weight is the dependent variable. The fixed factor is smoking, the extent to which the mother smoked. And the covariate that we tested in our correlation analysis is BMI. We're not completely done yet. We need to click on Model, click on Build Terms. We want to test smoking as a main effect. Go to the Build Terms box and make sure Main Effects is selected. Move it over. Click on BMI. Again, make sure Main Effects is selected. Move it over. Now press Control and click on Smoking and BMI, making sure they're both selected. Click on Interaction and move that over. That will set your interaction term to be tested in the model. Make sure Include Intercept in Model is clicked. Press Continue. Next, go to Options, click on Descriptive Statistics and Homogeneity Tests. Press Continue and OK. Regarding homogeneity of variance, the Levene's test is not significant at 0.892, which means we do have homogeneity of variance. Another way to look at homogeneity of regression is looking at the interaction term. We find that it is insignificant at 2.03. Since the interaction term between the two independent variables is insignificant, this shows that the independent variable does not have an effect on the relationship between the covariate and the dependent variable. In other words, any effect that the covariate has on the dependent variable is the same in all groups. So we're not concerned about homogeneity of regression based on the Levene's test and the interaction term effect. We have satisfied an important assumption for doing ANCOVA and can proceed to interpret the results. The model results are shown in the table Tests of Between Subjects Effects. It shows that smoking with a significance value of 0.131 does not have a material effect on birth weight. That is in the presence of BMI, which is a significant contributor to explaining birth weight. It has a p-value of 0.000. In other words, the covariate was significant, but the categorical factor of smoking was not. We determined that smoking is not significantly associated with birth weight after controlling for BMI. I hope you found this video to be useful. Thank you.